welcome back. So this talk, I will talk about the spectral geometric lemma that I hinted to in the first talk. So this is the main technical tool that we need in order to prove the finiteness results on the L parameter stack, which then go into proving that R psi preserves compact objects. Okay, so let me very briefly recall. So there's a version of the spectral lemma in representation theory, and I will not write down a precise version of this, just give a hint. So the geometric lemma for smooth representations. What does it do? Well, it expresses a composition of the form, have a JK functor and an induction functor. Okay, so you can form this for two parabolics in G, and then you can ask, can I express this in terms of the same functors but the other way around? And you can, and it expresses this in terms of functors of the form. So the other way around, but now just to the levy of P1, I induce from some levy inside of the levy of P1, and I first reduce. Sorry. Okay. So the precise statement is that the first functor that I wrote, this JK and induction, this has some filtration in terms of the functors that I wrote there. And we want a version of this for intco par G. Okay, and the applications of this you will see in the next talk by David. But roughly the idea is that when you want to do some sort of induction arguments where you induce from some levies to G, it's really useful to know how these compositions of functors work. Okay, and well, the argument of the spectral geometric lemma on the surface is actually not that difficult, but it's getting extremely technical for several reasons, and one of the reasons is that it needs some serious derived algebraic geometry and a good theory of incoherent sheaves. And both of these were not developed to the extent that we needed, or at least not in a way that we needed it. Oops. So we developed some stuff of that ourselves. And I will briefly summarize some of the main results that we recover for incoherent sheaves. And so let me just start with the main theorem here. So I introduced these incoherent sheaves just as the incompletion of coherent sheaves on par G, and it turns out that this is part of a full six functor formalism. And this works in quite some generality. So fix a regular Noetherian ring lambda. So in our case, this will be QL bar, but the statement doesn't care about this. And then there is a sheafy presentable six functor formalism. X goes to intco X on the category, which I will call stack lambda LAFP. So these are just stacks or derived stacks over lambda. And this LAFP stands for locally almost finitely presented. And I will not go into the technicalities of that definition, but it's roughly some derived version of finitely presented. And locally, of course, means only locally on some cover. And so what does a six-functor formalism mean? So, i.e., we have functors. I will just name them all once, and I hope that it's more or less clear what kind of functors they are. So we have a tensor and hom. So this lives on intco x for any particular stack x. Then we have an f upper star and an f lower star adjoint functors, and they exist for all f. And then we have another adjoint pair, f lower shriek, f upper shriek, and these exist for what I will call shriekable f in this talk. Okay. So if you've seen any reference on incoherent sheaves in the literature, you might be a bit confused because I'm using different notation from the literature. So I'll make a remark about this at the end, but let me just continue with this notation for now and write down some properties of this six-functor formalism. So, right, so the first, by the way, this sheafy just means that it has descent, and presentable just means that the categories are nice, so don't worry too much about these two words. So how do I construct anything in this intco? Well, one thing that's really nice about it is that there's
What's the tone
in FPPF. So for every x in my category of stacks, there is a functor gamma from qco x to intco x, and this functor is compatible with tensors and pullbacks. Okay, so that's already quite nice. No, yeah. What I call f lower star doesn't really exist in the literature, I think. Yeah. Wait for the remark at the end. I don't know, it's the notation I'm used to, so I'll make a remark for translation for anyone who has seen incoherent sheaves before, and it's not so bad. I just name things slightly differently, but it's the same functors. Okay, then next is, suppose I have a map f from y to x in this category of stacks, and suppose this is either QCQS schematic or some technical term, which I think in geometric Langlands is often called QCA. So what does this mean? QCA means lambda is defined over Q. The map is quasi-compact. It's representable on Artin stacks. Okay, but these are all the boring properties. The interesting one is that it has affine diagonal. Okay, the good thing about these is that they appear quite often. If you do something, for example, par G is a disjoint union of QCA stacks. That's the reason why we care about this. So in this case, so then F is shriekable. And so I have the full power of the six-functor formalism at hand. And also, I have some more precise properties in two cases, namely if F is proper, then the upper shriek functor coincides with the upper star functor, and if F is a local complete intersection or quasi-smooth, then F lower star agrees with the F lower shriek functor up to some twist, and that twist is given by gamma applied to the dual of the dualizing complex of F. in the sense of quasi-coherent sheaves. Okay, this might look very weird now because a proper map has upper Schwick equal to upper star, and this is again part of, well, this will be part of the next remark. So in some sense, this inconsistent functor formalism is somewhat dual to the quasi-coherent one in the sense that anything that's étale or smooth in inco behaves more like proper, and everything that's proper behaves more like étale. And there's a precise way of, of making this very precise, which I will not go into. You can ask me later if you want. But in fact, INCO is closely related to the actual dual of QCO solid, of solid quasi-coherent sheaves. And that explains all of these things, and that's also how we prove all of this. Okay, and then last, so if X is a QCQS scheme, or QCA over lambda, then this int co of X is really just int of co of X. And let me remark here, so this QCA requires lambda to be in characteristic 0, and let me remark that in positive characteristic this fails, unless you put some much stronger assumptions on this. So in particular, this theory doesn't work very well in characteristic L if you want to apply this to the L parameter stack. But in characteristic 0, it works quite well. And that's all we need in this paper. OK, so let me make this one remark. So if you've seen other sources on incoherent sheaves, so in cases, so what do these functors actually do, these 6 functors? So in cases where, or sorry, just say in case C. So in the case where int co is really just int of co, you can ask how these functors are computed, right? And then, so suppose I have some map where both of these are now int, so in the case of C. And then so if F is LCI, then this F upper star, which now goes to, int of co of X to int of co of Y, and this is the int extension of the functor F upper Schwick going from co of X to co of Y. Okay, and under the assumption that F is LCI, this F upper Schwick actually preserves coherent sheaves, so this makes sense. And similarly, if F is proper,
this is not the same F upper Schwick as
this is the upper Schwick. So this is the upper Schwick that from QCO solid, I guess. Like, is it not?
It's like the dual L, the growth can be star truncated, naive upper star.
Yeah, isn't that this one?
I was just mentioning it in case people were confused because there's already upper Schwicks.
Yeah, so this upper Schwick is not the upper Schwick from INCO. It's the upper Schwick that you might define more more classically.
Like residues and duality.
Yeah, right. It's the most basic upper Schwick you can define. So, and in the proper case, I got here, the F lower Schwick, on INCO as the int extension of the F lower star, because in the proper case, the low F lower star preserves coherent sheaves. Okay, so this is understandably very confusing. So that's why in the literature these functors are often denoted differently. So often this tensor product is denoted by a tensor product Schwick. The F upper star is often denoted F upper Schwick INCO, and the F lower Schwick is often denoted F lower star INCO. Okay, so I guess these notations on the right, they indicate how you actually compute the thing. And the notations on the left, they indicate what role these functors play in the six-functor formalism. And unfortunately, these two things don't match. So you have to choose either of these two notations. And since I come from six-functor formalisms, I prefer the notation that makes it clear what these things do in six functors. But if you're more on the computational side, then you can think of these in terms of the classical notation. Okay? Everyone confused now?
So does this mean that in the classical setting, there are actually two six-functor computers?
Yes, there's one on QCO-solid, on solid coherent, quasi-coherent sheaves, which behaves exactly the way you would expect. Like étale maps or smooth maps are cohomologically smooth and proper maps are cohomologically proper. And then there's this INTCO, which is somewhat dual, where everything is weird, like because everything is swapped. Yeah, it is what it is. I can't change it, unfortunately. But at least as long as you stay abstract and formal, it doesn't matter so much, right? Because you can just play around with these functors and they behave exactly the way you like them, like from the six-functor perspective. Only when you try to actually compute something, it gets very easy to get confused because there's often twists by these dualizing complexes inherent in all of this. And one has to be very careful with understanding what one is actually doing here.
When is this functor gamma fully faithful?
I think it's fully faithful if your scheme is LCI, or more generally SWAF, or whatever you want to call it, eventually co-connective. Yeah. Okay, so this more or less already existed in the literature. Except, okay, we're more general here because we allow an arbitrary irregular Noetherian ring. I think all previous references worked over an algebraically closed field in characteristic 0. Right, and also, yeah, okay, let me stop at that. But so we generalize this and we give a completely new construction of this based on condensed mathematics, which gives most of these properties for free. But then what did not really exist in the literature before, and what we really need, and which is part of why we develop all of this stuff, is an excision sequence for incoherent sheaves. So how does that go? So suppose now that I have a closed immersion of stacks. So same setup as before. And then I consider the completion and that closed immersion. So I will call this an immersion I hat. And then there's an open complement U. So this is the open complement. Okay, and then for all sheaves in int co x, we have the following statement. So first of all, there exists a fiber sequence of the form. Okay, now it gets a bit confusing again, maybe, because it might not look the way you're used to. Okay, so I have an excision sequence like this. And usually you would expect these functors to be the other way around, j in the front and I in the back. And there's nothing I can do about that. But the fact, again, like this closed immersion behaves like an open immersion for intco, and that's why you have to put it on the first part, and vice versa. Okay, so we have a fiber sequence like this. So this is the usual excision sequence, and it does hold in intco. And moreover, so if we have, if I denote by Zn the nth infinitesimal neighborhood of I. So if I is given by some ideal big I, then the Zn is given by this big ideal to the power of n. Okay, so the usual thing. Then I can write this functor so the left-hand guy, because right now it's a bit unsatisfying, right? Because in usual excision sequence, you see, okay, the J on the one side is fine, but on the other side I see this weird I hat, and I don't want that because I start with my closed immersion I, and I really want to express this part in terms of I somehow, because this is the one that we can control at the end. So here I can tell you how to do that. Namely, first of all, this first part in the excision sequence is just a colimit over the pole shriek to all these infinitesimal neighborhoods. Okay, so that's good. And now we need one more thing, because that's still talking about these infinitesimal neighborhoods, which I also want to avoid. So we can avoid this with the last piece. So if I denote by n m 0 over x, so this will be the normal bundle. So formally this is the cotangent complex shifted, dualized. So this is some quasi-coherent sheaves, quasi-coherent sheaf in Z. Okay, so this is just it's the sheaf that represents the normal bundle of Z inside of X. And if this is perfect, then it allows me to compute the cofiber of two successive terms in this colimit that I have up top. Okay, so if I take two successive terms, then the cofiber is just F tensored with I lower shriek gamma of the symmetric power, the power of n of this normal guy. Okay, so now note that the thing on the right-hand side and the bottom really only depends on I now. It has nothing to do with these. Sorry? Bigger. Like this? Yeah. Okay, great. Okay, right. So I think this is a somewhat folklore statement that is implicitly used also in some geometric Langlands papers, but it was, as far as we know, not recorded in the literature like this. There's one proof of some part of this, which I think is wrong, and that's all we found. So we proved this. I guess to say, so the one of the essential difficulties you have in this statement is if this I is not a regular closed immersion, because then things become weird when you talk about these infinitesimal neighborhoods. So first of all, well, everything is derived here, so you need some notion of infinitesimal neighborhood that works in the derived world. So you need to define powers of an ideal. And if that ideal is not a regular ideal, things get, like, you can define it, but controlling it becomes a bit tricky. And that's what we do. Okay. Any questions about this excision or incoherent sheaves? What excisions work quite generally in Etal or Motivik or whatever. In QCO solid, I guess in QCO solid you can expect something similar to this. Like the hard part about this proof is the geometry, like really understanding how this completion relates to these infinitesimal neighborhoods, defining them in the first place and showing how they relate in the derived world. Yeah?
How do you see the form of completion?
How I define it, or?
As in whether it's like a formal stack or?
Well, by definition, it's just a substack of X of all those maps that factor on the topology over the closed subset C. That's one way to define it. And inherently in the statement is some sort of statement along the lines of that this completion is roughly the co-limit over these ZNs. Unfortunately, that's not literally true, but it's close enough. It's true close enough so that we can make the statement work. Okay. Then that's all I wanted to say about this INCO stuff and this formal nonsense. And now I want to come back to the L parameter stack. And the first thing I want to do is talk briefly about the Eisenstein and constant term functors, because those will be the one that replace parabolic induction and Jacquet functors. So let me briefly mention those. Okay. So we fix G as before. And I also fix some Maximal Torus, some Borel. And from now on, I'll stick with lambda being QL bar. And so what are the Eisenstein functors? So for any standard, I guess semi-standard parabolic P equal to mu inside of G, I can define this stack par P, which is just defined in the same way as usual. So it's roughly maps like this. And then I mod out by the conjugation action of the dual parabolic. Okay, so there's no difference to reductive groups. But let me remark one thing, like I think, so this was discussed last week. In the case of reductive groups, this stack happens to be non-derived. So you can just study classically, but in the case of parabolics, this thing will be derived in general. So that's why we need all this derived algebraic geometry stuff. But if you look at it as a derived stack, it's still very nice. It's still LCI. It's not smooth, but yeah, still locally complete intersection or quasi-smooth. And so from this, we get a diagram par M, par P, par G. Okay, and then we define the spectral Eisenstein functor. Just, well, you pull from par M to par P, and then you push down to par G. And in classical notation, this is the same as this. Okay, so this goes from par M to par G. And then the constant term is defined just in the other way. So, and I will only write this in one of the two notations now. So this goes from par G to par M. Okay, so let me make a few remarks. So first, okay, I already said that par P is generally derived in general. I will not write this now. But also G, so this map from par P to par G is schematic and proper. And F is LCI with trivial dualizing sheaf. And this simplifies a lot in general. I think we've seen this Eisenstein functor before, last week in David's talk. And I think he just defined it as an incompletion of pull and then lower star. And because of these properties, that's the same as what I just wrote. I think from a maybe formal perspective, writing it in terms of the 6 functors is quite useful, because we will see later that that's the language that we need for this geometric lemma. But really what's happening under the hood is something pretty simple. And in particular, so if I stay in the 6 functor language, I can also phrase this as follows, namely that this f lower shriek is equal to f lower star, and this g upper shriek is equal to g upper star. Now, in terms of the incoherent 6 functor formalism, this just follows from these properties that I wrote before, and this immediately implies that in fact this Eisenstein functor is left adjoint to the constant term functor. Okay, so this is a really crucial property that will be used extensively in the next talk. And this also implies, quite formally, that this preserves coherent sheaves. Because the coherent ones are the compact ones, or at least with quasi-compact support. And if you have a functor that's left adjoint to a functor that preserves colimits, then that functor must preserve coherent sheaves. Compact objects. Okay, and it will be a crucial question, I guess, and probably in the next talk, what we can say about the constant term functor in terms of coherent sheaves, where it's much less clear how it behaves on those. Okay, any questions on this? Okay, so I've introduced these Eisenstein and constant term, and then there's one last ingredient I need in order to state the spectral geometric lemma, central grading. If I recall, this has not been discussed last week, so let me briefly give a definition. So there is a canonical central action so I guess central action is the name of this action, so it's just an action of the classifying stack of the center of G, and then the Weyl invariance acting on par G. Okay, so what does this mean? Well, if I have a classifying stack of something acting on something else, then on points it doesn't do anything because there's only one point in the first guy, but it does something on the automorphisms. And the automorphisms in par G are exactly the centralizers of L parameters. And so this action is just multiplying those. So this is just given by multiplying multiplication by the multiplication map of the center. And this S phi was the centralizer of some L parameter phi, and I can multiply by an element in the center because that will certainly line the centralizer. Okay, and now having this action, I can apply intco to it. And then this will act on intco of par G. Okay, but now the Z of G hat is, well, it's essentially some sort of torus, maybe up to some finite groups. And so by Cartier duality or whatever you want to call it, one can explicitly describe what this category is. It's just a direct sum over all the characters of just Q bar modules. So it splits in isotypic components. But now I have an action of this category of just this direct sum category on some other category, and this immediately induces a decomposition of that other category. So this induces a decomposition over the same chi. And then this is a subset. So this guy here, this chi component, is just those f in intco, such that if I act on this by O of chi, then I get the sheaf back. And I haven't had said what O of chi is. So in here, maybe that's. So I have this decomposition, right? And so in here, I choose a generator, which I call O of chi. So it's just the isotypic sheaf. The one where the action is given by the character chi, viewed as a z of g hat representation. Okay, so why do I care about this weird grading? Well, first of all, it will appear in a second in the geometric lemma, but also we already know that on the other side of the Langlands correspondence we have a similar grading, namely this reflects the decomposition, decomp of Bungie into connected components. Okay, because they are also parameterized by the same chi's. And so d of Bungie also splits canonically into a product or direct sum of d of Bungie sitting on each of these connected components. So whenever we want to make an argument on the spectral side that reflects something on the automorphic side that works with these connected components, we should expect to have to do something with this central grading. And that's why it plays such an important role in many of the constructions. Okay, so now I can finally state the spectral geometric lemma. Okay, so, unfortunately that thing is a bit technical, so I have to introduce a bit notation, but it's not so bad. So we fix two standard parabolics, P1 and P2 inside of G. And I should have given, call this M1, U1. So the Levy and the unipotent part, I give some names to them. Okay, and we want to compute functor, which I call f. So this is just the composition of the spectral constant term along P1, along P2, and the spectral Eisenstein along P1. So this will now be a functor from intco par M1 to intco par M2. Okay, and you will see in the next talk why it's very important to compute this. So for now, I hope you have some intrinsic interest maybe in trying to understand how the representation version adapts to this. Right, so how do we compute this? So we want to compute this in terms of Eisenstein and spectral terms of parabolics inside of the M1 and M2. So let me introduce those. So first we let W, W1, W2 be the Y groups of G, M1, M2, and then for an element in the double quotient, I introduce a bunch of more groups. So this HW is just the intersection of P1 intersected with W inverse P2 So this is the stabilizer of the Brihas cell associated to this W by the Brihas decomposition. I will write this in a second. And then Q1 is just M1 intersected with W inverse P2. And Q2 is equal to W of P1 intersected with M2. Okay, and then Qi is a parabolic in Mi, and let's call the Levy Li. So that's a lot of notation, but unfortunately all of this organizes into one big diagram. So on the top I have the L parameter stack of this HW. And then on the bottom I have the L parameter stack of M1 the L parameter stack of Q1, then the ones of L1 and L2, and they are isomorphic via this element W. Okay. So best case scenario, okay, we will see in a second that this power HW that appears at the top, this will show up in the computation of the functor f. And the thing that we want to see at the end is the composition along the lower line, which is because you see the first thing is just an Eisenstein functor, and the second thing is a constant term functor. The other way around, I guess. Sorry, yeah. So first was a constant term functor, and the second is an Eisenstein functor. Right? So in the usual geometric lemma, what you see is a filtration of the functor you start with by exactly the compositions along the lower part of this diagram. And so we want something similar. And so how do you do this? Well, if I compute the composition along the lower diagram, what will show up is this Cartesian product here, right? This Cartesian product, unfortunately, is not par HV, but it is something else. It's something that I will just call par W. I will just call this par KW. And this can be, in general, not the same as this HW. So there's some projection, but it's still the L parameter stack of some group. And let me just give these guys some name.
Then your handwriting is getting smaller again.
Sorry. Well, I mean, there's a lot of stuff I need to fit on one screen, unfortunately.
Is this a vertical arrow?
This is supposed to be an HW. Zoom in even more? No, but like if I keep doing that, then no. Okay, so we have this diagram. So how does the classical geometric lemma work? Okay, it's probably often not phrased this way, but roughly what happens is you take the computation along the lower, the composition of the lower map in this diagram, so this lower zigzag. Then you show that's obviously the same as first pulling to KW and then pushing down. And then what happens magically in classical geometric lemma is because this HW is a pretty stupid map. I mean, it has unipotent kernel. You can easily check that. And so what you would actually have to do is also pull up to HW and then push all the way down, right? So in classical, so you pull here, then you pull up, then you push down, and then you pull here. That's the functor that appears in the filtration naturally. But classically, this pull and then push doesn't do anything because this has unipotent kernel, and the homology of unipotent groups is trivial. Unfortunately, this is not what happens here because unfortunately, this thing is far from being trivial. So we need some way of controlling this pull-push along this map. Okay, and so, for example, the kind of thing that you should expect to appear here is this KW could be some sort of torus, and this HW could be a Borel. I think this is what happens in the case. If you do, in the simplest case where you do this with GL2, you should think that this KW is a torus and this is a Borel. And so the kind of push forward I see is some sort of push forward from par B to par T. So this kind of thing I need to control. Okay, and now comes the statement.
Sorry, for the definition of these groups, do you need to choose a representative of W?
Yeah, probably. I guess I choose a minimal length representative. Right. I haven't defined KW. So one way to define KW is it's the one that fits in here. So that would mean it is the fiber product of Q1 over L1 with Q2. There's also another way to define it, namely as HW modulo the intersection of the unipotents in P1 and P2, or W inverse P2. And from that definition, you see immediately that the kernel is exactly this intersection of unipotents, and that is unipotent, but unfortunately not trivial in general. Okay, so here comes the spectral geometric lemma. So the precise formulation is a bit technical, so I'll try to formulate it in the easiest possible way. So at the end, we have our functor f, right? We want to compute our functor f, and we want to decompose it into simpler pieces. And the statement will do that, even though the way we decompose might be a bit complicated. Like, the only thing that's really important about the statement is that at the end, the pieces are pretty simple. So that's the whole point of this lemma. And the way you decompose is as follows. So first, check that f has a filtration indexed by this double quotient. And then the graded pieces I will call FW. Okay? So in the usual geometric lemma, this is where you stop, and now you just describe these FWs as something simple. We have to go further. So each FW has a N filtration. Okay, and then this I can also write. So then this has some gradeds, and these gradeds I can denote FWN. Okay, now you could hope you can stop here, but unfortunately we have to go one step further. So now this FWN I can decompose further. This is just, but this decomposition is pretty simple. It's just a decomposition as a direct sum. This one is optional, but well, in some sense we need it, right? Also, if I want to do the final statement, I have to talk about these guys. So it's a direct sum of these guys, FWN chi for chi running through characters of some group ZW, and the ZW is just the center of KW, and you can also write this as Z of M1 hat WF intersected with. So this is a pretty concrete group. Just intersection of the centers of M1 and M2. Okay, now I have decomposed my F into these FWN chi, and now I can start trying to understand what these are. So I can explicitly write them down. So this FWN chi is FW composed with W lower shriek of KWN chi. Maybe I shouldn't call this K because I already have a group K. Let's call this G. Tensored GW upper star. Okay, so if you look back at the diagram, okay, so for some G, W, N, chi in int co par KW. Okay, so if you look at the diagram, so these FW and chi, they now are pretty close to what we want, right? So they're computed in terms of pulling from M1 all the way up to KW, then twisting by some weird sheaf G, W, and chi, and then pushing down. Best case scenario is this G, W, and chi is just trivial, and then pulling and then pushing is just the same as the functor that we actually care about. Unfortunately, that's not what happens. Even after decomposing in 3 steps, these things are still not trivial. But we can say something about what they look like, at least in the cases that actually matter at the end. So I need to make one more restriction, namely either M1 is Q1 or M2 is Q2. Then I can say more about these sheaves, namely, in this case, all of these G, W, N, chi are perfect. And also, very importantly, if I fix W and chi, then these G, W, N, chi are 0 for large enough n. Okay, so we have some good bounds on these. So they're all perfect, and most of them vanish. But still, there's a bunch left. Okay.
What is W? Like you have an FW composed from W?
It's just the isomorphism given by twisting by this Weil group element. It's an automorphism.
L1 and L2 are identified by dual W conjugation. So that isomorphism in the bottom middle.
So this is, yeah, but I guess I need it up top, right? On here.
Yeah, you actually work with KW and it's W conjugate. And
Ah, yeah, sorry, yeah, I guess implicitly implicitly here I have also the W inverse of KW, and that actually is the one that projects to Q2. Yeah, thanks. Okay, so this is the statement. And so the statement is quite technical, but once you have all the tools available, the proof is actually not so bad. So I will briefly sketch why you should believe the statement. And actually, so this also proves the usual geometric lemma, I guess, which is, yeah, along similar lines. So for simplicity, I will assume G is split. But this doesn't change the proof, it only changes the amount of notation that I have to put everywhere. So one thing this case simplifies is that if G is split, then this par G, so we need some way of accessing par G in a slightly more conceptual way than if I just write it explicitly as something modulo conjugation by G, or by G hat. So I can write this as the mapping stack, in this case, the classifying stack WF, and the classifying stack of G hat. And you need to be slightly careful, so maybe let me only say this. I mean, it is true literally if you are careful with the condensed structures, because this WF is a condensed group, and so you have to put some condensed structure on this G hat, and there is a way to make this precise, and I will not go into that. But roughly, it's just this mapping stack, right? And you can make this precise if you want. You can also discretize the Weil group and then pass through the usual construction to make this precise as a mapping stack. Okay, but note that in this mapping stack, this modding out by the conjugation of G hat is inherently already given. And that's good, because now I need a way to handle the following fiber product. So as I said before, oh no, I didn't say this before, but so now F is given by so I just write down this fiber product par M1 goes to par P1 goes to par G goes to par P2 goes to par M2. And so the functor F is given by the composition of these lower maps. And well, this is also the same as just pulling all the way up to the fiber product and then pushing down. But now what is this fiber product? Well, this is the mapping stack of the Weil group to the fiber product. To the fiber product of the classifying stacks of G hat and P1 hat, and this is just this double quotient space. Okay, so this is purely formal. And now the idea is, using the Brihard decomposition.
You want to say F is given by like full push?
Ah, sorry, yeah. So F is given by, thanks. So F given by, what do I call these guys? F. G. So F is given by just G lower shriek F upper star. Okay, and so I used the Brihart decomposition. The most classical one you can think of, at least in the split case, to stratify. Well, first of all, I can stratify this P1 hat mod G1, G hat modulo P1 hat and P2 hat, right? Because this is really just a double coset space, and hence, okay, there's a small technical thing you have to check that this stratification extends to X, to this mapping stack, but that's okay. And then this stratifies this into locally closed strata XW inside of X, and this XW is isomorphic to par HW, and the reason is simply that this HW is exactly the stabilizer of the Brihart cell corresponding to this W. So this is again for W.
This is really a topological stratification.
Yeah, it's really a topological stratification. So these are locally closed subsets, and they have all the nice properties that you expect from a stratification. Okay, but now we're almost done, right? Because so now we go through the excision thing. So by excision, so by iterated excision along the stratification,
The W modulo F, W1, W2.
The middle W should be.
oh, sorry, yeah, thanks. So by iterated excision, we get the filtrations on F. Okay, so let me scroll up a little bit to say what we mean. So we have two filtrations. One is by this W1, by this double cosine set of W's, and then the other one is N. But both of these appeared. So the one over this double coset space is coming from the stratification of X, and the one over N is coming exactly from this here. Okay, and this allows us to stratify the functor, because a priori in the fiber sequence, the things that I would get are the completions of these XWs and X, and these are hard to handle. But then using this colimit here, I can break it down into pieces that look like this, and the graded pieces, which are the ones I wrote here, they are now just given by this. And this only talks about the XW, so the things that I can control, just the L parameter stack of HW. And then the only thing that's left to control in the final statements is this guy here. So we need to compute the cotangent complex of the XW inside of X, but that's not so hard. And then we need to understand which characters appear in there. So also, right, there's this one step that I forgot to say. So this decomposition into these F, W, N, chi, this comes from the central action. Now I have the centra ZW on this par KW. Okay, and now finally, so this gives us all the statements up until here. And now these two are left. And these two, I will not say so much about this, but if under the assumption that M1 is Q1 or M2 is Q1, so if M1 equal Q1 or M2 equal to Q2, there is a contracting A1 action on HW to KW, and then we use some form of contraction principle along this. Okay, so let me just scroll up again slightly. So we had this map HW that we need to control somehow. And under these assumptions, if H1 contracts onto K1, if HW contracts onto KW under some A1 retract, roughly what's happening is that if you push along this map, it's close to just pulling along the section of KW into H1. And the arrow you can bound quite explicitly. And that's what we do to get this final piece here. Okay, I hope this wasn't too technical. And in the next talk, you will see all the cool things one can do with this. Thanks.